Alright, we're looking at ionic compounds and how they are formed, and how we can use a Lewis dot diagram to model that compound. So let's start with a simple one like number 1. We're going to look at the combination of potassium and fluorine. So I'm going to begin by just drawing a Lewis dot diagram of each of those elements. So potassium, if I look at the periodic table, has, whoa, what happened there? Sorry about that. Potassium has 1 valence electron, and fluorine, if we look at the periodic table, has 7. Again, when I draw my Lewis dot diagrams, I'm going to draw them in pairs on all 4 sides of the element. So I have potassium and fluorine. Fluorine has very high electronegativity, and potassium has low electronegativity. As a result, fluorine is basically going to pull this electron over here. So I'm going to model that with an arrow. The result of that, now potassium has lost its 1 valence electron, and it fulfills the octet rule because now its next energy level, the one that was below that, is now full because its previous valence electron or valence shell is now gone because it's lost all of its electrons. But it has lost 1 electron, so the result is a positive ion. It has a charge of +1 because it lost 1 electron, so it has 1 more proton than those electrons. Fluorine, on the other hand, has gained an electron, so it has a negative charge. So when I model this, I'm going to show the process of the electron moving from potassium to fluorine, and then I'm going to show the end result of that. And that is fluorine with 8 valence electrons and a -1 charge, and potassium with a +1 charge. Let's look at a more complicated example. Let's look at number 5. So we begin with aluminum. Aluminum, when we look at the periodic table, has 3 valence electrons. Bromine, again, when we look at the periodic table, has 7. While you're working through, it helps to count valence electrons, because again, we want to think about the octet rule. Valence want to have the electron configuration of a noble gas, which is typically 8 valence electrons. Don't forget about helium, though. Helium only has 2 valence electrons, so it's happy with 2. So bromine, again, high electronegativity, wants 1 more electron, so it's going to take this electron over here. That makes bromine nice and happy. It has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Aluminum, on the other hand, is still wanting to get rid of 2 more electrons. So it's going to do that by giving it to another bromine atom. And that bromine atom has 7 valence electrons. Should have put a little bit more space in there. Now, aluminum still wants to get rid of this valence electron. Bromine has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, so that bromine is happy. But aluminum needs to get rid of 1 more, so it's going to give it to another bromine atom. Again, it has 7 valence electrons, so now this electron will go over here. Now, each bromine has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and aluminum has gotten rid of its 3 valence electrons. So my aluminum atom has a charge of +3. It has lost 3 electrons, which means it has 3 more protons than it does electrons. And then bromine, each bromine has 8 valence electrons and a charge of -1. So again, it's a 2-step model. The first part of the model shows the arrows, which indicates that the electrons are leaving the cation, the positively charged ion. They're leaving that and going to the anion. And then the second step of that model shows the end result. After those electrons have moved, Now I have an ion. Aluminum with a positive 3 charge, and 3 different bromine atoms, each with a negative 1 charge.